destination has received the message, then the protocol won't end in this state, won't be successful. And so my definition of security has to do with tolerance, tolerating a gamma adversary. So I'll say that this protocol, say this routing algorithm, whatever it is, P, tolerates a gamma adversary as defined just now if the probability that the protocol terminates when the adversary is active is the same as the probability that it terminates when it's passive. And that means essentially that the adversary has not achieved anything. The protocol is equally like this, for the probability that it succeeds is unaffected by whatever the adversary does. So the adversary might as well stay quiet and not do anything. And that's sometimes called the sort of perfect tolerance, gamma tolerance. I may allow certain cases where the tolerance is not perfect, where there is a small error probability. So the adversary gains a little bit, but if epsilon is small, this is the next one, so it's less than epsilon. That means that what the adversary gains by taking part in this protocol, by being active during the sort of the execution of the protocol, is a little bit, but not enough to affect in any practical way the protocol. I can also talk about computational tolerance, and that is when the two probabilities are they're not equal, but you cannot distinguish them using polynomial time procedures. Just for practical reasons, this model differs, my approach differs from the traditional one where you normally would want an application to be reliable. You would say that a protocol is reliable if it succeeds 100% of the time. In the kind of work I'm working here, even if it succeeds 75% of the times, that would be acceptable. In the real world, sometimes you could almost convert a 75% to be almost 1. The question is, the cost in so doing may be very high, and if your nodes are bounded and all your resources are bounded, maybe you can just settle for 75% of the time. Okay, so now I'll get back to the kind of algorithm I'm working with. This is these are sort of these routing algorithms, which on which and a lot of work has gone on in this area, and most of the routing algorithms which have been sort of proposed have certain very advantages and offer certain. Some are more flexible in some ways, others in other ways. Essentially what you could do is you could classify them in two categories: those which are network-centric and those which are source-centric. Network-centric algorithms rely on the sort of rely on the algorithm in which the routing effort is distributed. Everybody helps out. So when you want to send something, what you do is you just send information about whom you want to send it, and your neighbors already have sort of vectors. They know how to send it forward. So it goes on without the sort of the source having to do too much work. The work is done on the way to the destination. There are a couple of algorithms in this category: DSDV, WR, and AODV. AODV sometimes falls in both categories. The second is the one in which the source does all the work. The source does the work to find out the best path, the shortest path to the destination, and the nodes on the way to the destination do the minimum. They just forward the message when they get it. From a security point of view, the source-centric routing is better, is less vulnerable to malicious attacks. And the reason for this has nothing to do with ad hoc networks. It's outside ad hoc networks. It has to do with the way trust infrastructures are linked together. So, for example, if you want to do something and you want to do it in a secure way, the best way to do it is to do it yourself. You never delegate. The moment you delegate something, there is a risk that the person you have delegated to may be untrustworthy and may not do it. But If you do it yourself, then you can trust yourself. So the less trust you put in the others, the more secure in general, the less vulnerable the system is. Security mechanisms. The protocols one uses in distributed applications will always involve some crypto. And crypto comes in two flavors. Symmetric key crypto and public key crypto. Symmetric key crypto is usually much cheaper. Public key crypto is more expensive. But there are cases when you have to do with public key, you can't use secret key. If you want digital signatures, it has to be public key. If you want to have a way in which your nodes can be authenticated in the system, you have to use digital signatures. So wherever possible, one uses MACs, message authentication codes. MAC here stands for message authentication codes, which can be used combined with a secret key to get what is called an HMAC, and that you can use for integrity checks in a limited way, and you could also use encryption schemes that way. So the problem with the digital signatures is comes in sort of it has not to do so much with the digital signatures. It has to do with a problem which public key crypto systems have, and I'll try to describe it. So the first thing is this. To be able to identify nodes in the system, at the beginning of the system, each node is assigned a secret key, is given a secret signing key, and also a list of the public keys of all the others. That's why I somehow avoid the trusted key infrastructures. So a node has kept a list of all the public keys of everybody else and its own secret signing key. So it can sign, and using the public keys of the others, it can verify everybody else's identity, for example, or link a message to an entity. So digital signatures then can be used to link messages which are signed by a node to the node who signed them. This all works perfectly well and keeps this kind of link, one-to-one link, except that in a malicious environment, if you have cheaters, they don't need to follow the rules. So what malicious nodes may do is they may start sharing their keys. So if there are 5 malicious nodes, they each share their 5 keys, and one malicious node now can present itself as 5 different people, 5 different nodes. And this creates a problem in a mobile ad hoc network, because the only way to deal with other people is through what you get from them. So if you get 5 signed messages by nodes who all claim to be your neighbors, you must assume that that is the case, whereas in fact only one node is there signing on the behalf of the 5. This is sometimes referred to as the Sybil attack. So this is what one has to take this into account. This is one of the threats, and whatever secure protocols have to be designed, they have to be designed with this in mind, with this kind of threat in mind. And as I said, the problem is that you cannot link an entity uniquely, bind a physical node to an entity by using public key cryptography. This is not a problem of mobile ad hoc nexus. It's a problem of public key cryptography. You can't do it in any other way. If you decide to share your secret key with your wife, then your wife can pretend to be you if in this kind of wireless environment. There are 2 general attacks which can happen in this environment, due, of course, to the malicious behavior of the adversary. And I've grouped them into 2 categories, and most of all the attacks fall in these 2 categories. The so-called denial of service attacks and the man-in-the-middle attacks. Denial of service attacks are sort of the straightforward attacks. They are the attacks in which the adversary triggers some kind of event which results in the network not being able to provide the service it is supposed to provide. And usually this happens by flooding the network with irrelevant packets. That's malicious.